Swayam Prabha. Digital India. Educated India.
To one fundamental equation based upon the conservation of linear momentum, we were able to get our Navier's equation. So using the Navier's equation, we were able to arrive up the system of membranes. Now, membranes and plates are the two basic problems that we look up in solid mechanics in terms of vibrations and analysis, bending and vibrations. So, membranes are one dimensional or two dimensional based upon whether they are considered as a string or a membrane. So, a string is a thin thread or wire which is fixed at 2 points, and that is one dimensional. Its thickness dimension is ignored. It does not have a depth dimension. Likewise, a membrane is 2D, but its thickness is negligible compared to its length and depth. So, membranes are different from plates. We will come to plates eventually in today's lecture. Within a membrane or a string, we have looked at situations which is one dimensional. So, a string with the application of a uniform load which causes a deflection. We have tried to use our Navier's equation and the variables of displacement to find out what have been the displacement for a fixed string under a given applied pressure or load. In the last lecture, we ended up by initiating some discussions on this membrane with a concentrated load. So, concentrated load would be that this is a membrane and we put a point load at the center that is concentrated at the center, and that is causing the membrane to deflect. So, it will form something like a triangle, and that point load analysis is what we have been trying to induce. Okay. So, a point load is induced by some actuating mechanism. It can be a pin acting on a membrane, say you are doing atomic force microscopy, and then these are relevant topics related to some of the characterizations or measurements that we do. We have a cantilever beam on the surface of an atomic force microscope, and that is moving over the surface, and the surface can be soft, say a polymer. In that case, those deflections on the surface due to the impact of the pin of this AFM tip would be causing some of these deflections, and that is what we are trying to study. Okay. So, we started with this Green's function is given by del square g by del x square plus delta x 0. It represents a point force of unit load on the given string. So, this is a point force which is acting on the string at a given load. Now, it is acting at a point x naught, where we have x is our x axis on which the string is held. Our Green's function equation is this as defined over here, and the solutions for this is such that we meet the boundary conditions. So, we have assumed that the center of the string goes to x is equals to 0, and at x is equals to minus half and plus half is where the string is pinpoint. So, at x is equals to plus 1 by 2 and x is equals to minus 1 by 2 is where we have those pinpoints for the pin. All right. Now, we go into trying to get a solution for this g. Now, it is a second order derivative. So, at x naught equals to x 0, we have 0 values for g or del square g by. So, this del x minus x naught is our direct delta function, and that is equals to 0. When we try to solve for this direct delta function, we get two solutions, right, and that is one before x equals to x naught and one after x equals to x naught. So, from minus 1/2 to x naught, we have a x plus b, and plus 1/2 to x naught, we have c x plus d. Okay. Now, we have 4 constants, right, 2 constants for before and 2 constants for after. When we impose our boundary condition, so this is our boundary condition onto our equation. So, we will get that one of the constants will go away. The first equation becomes a x plus 1 by 2, and second equation becomes c x minus 1 by 2. Now, we are left with 2 constants. That means that we need 2 more equations. Okay. So, the second constant or the second set of constants so we need a slope boundary condition. and a continuity boundary condition. Right. Okay. We can say that g value at x naught minus should be equals to g value at x naught plus. This is our continuity at x is equals to x naught. So, our function should be continuous from left side to right side, it should have the same value at that point. So, we can say and from the slope, since our equation is del square g by del x square plus delta x minus x naught is equals to 0. We can integrate this once. So, integrate once about x equals to x naught plus minus, we will get dg by dx. So, we are integrating this with the limit of x naught minus to x naught plus, right, about x naught. So, we get x naught plus minus dg by dx at x naught minus will be equals to minus 1. Integration of the direct delta function over x naught is 1. So, you take it to the right hand side and becomes minus 1. Okay. Now, we have these two equations and these two equations can satisfy our two of the boundary conditions. So, let us put the second equation and our dg by dx value. So, we take g from here and we substitute into this derivative. First derivative will be a and c. So, we can see that c minus a is equals to minus 1. So, this is one of the conditions we can get out of it. So, the first equation that we can get is c minus a equals to minus 1. For the second equation, we will take our continuity about x naught. So, using our continuity about x naught, we can get that a of x naught plus 1 by 2 is equals to c of x naught minus 1 by 2, right, at x is equals to x naught. Now, we can substitute the condition that c minus a equals to minus 1. If we substitute this, we get c plus 1 into x naught plus 1 by 2 equals to c x naught minus 1 by 2. And if we simplify this, then c comes out to be minus x naught plus 1 by 2 and a comes out to be equals to minus of x naught minus 1 by 2. Hence, our net Green's function equation for a point load is g of x is equals to minus x naught minus 1 by 2, x plus 1 by 2 and minus x naught plus 1 by 2, x minus 1 by 2. This is from the domain of minus 1 half to x naught and this is from the domain of x naught to plus 1 half. Okay. So, this is a set of the equations that we get. We can see that the equations look very symmetric in nature on both sides, and this is the solution that you will get if you have a concentrated point load of unit magnitude at that location, right. If you have any other magnitude apart from unit magnitude, you can just multiply the magnitude with the direct delta function. Direct delta function gives you 1 as an output. If you have say 10 or 100 units of force, whatever unit of force or the unit of the equation that you are solving, you can just directly multiply it with the direct delta function. Okay. Now, if you want to reconstruct this with a variable load solution, so considering a variable load, p is a function of x such that d squared u by dx square plus p of x is equals to 0. Again, u at plus minus 1 half equals to 0, and we want to get a solution for this using our Green's function method. Then our Green's function equation, let us write it again, d squared g by dx square plus delta x minus x 0 equals to 0. Again, g at plus minus 1 half equals to 0. Okay. So, we are using the Green's function method to solve for this variable load. So, Green's function gives you segment by segment point loads at that x naught condition, and Px is a variable load, right. So, what we do is we are trying to integrate the difference of the u and g equations by multiplying the reciprocals. Okay. So, we multiply the first equation with g, we multiply the second equation with u, and we subtract both of them, and then we take an integration within the limit. So, our integration from minus 1/2 to plus 1/2, and we are getting g of x d squared u by dx square of x d squared g by dx square plus p of x into g of x, x at x naught also. See, we can see that g is a function of x and x naught from here, and minus our u of x, and then the direct delta x minus x naught. This dx we are trying to get should be equals to 0. That is the objective of this equation. So, let us write this equation one more time on a fresh page. So, minus 1 by 2 to 1 by 2. Okay. Now, if we try to integrate this by part, integrating by part, you can give it a try yourself. What you will get as an outcome is that u at x naught will be equals to integral minus 1/2 to 1/2 p of x g of x comma x naught dx. Since both x and x naught are variables, where x is the domain variable or the spatial variable, x naught is a location where the load is being applied, we can exchange x and x naught. And we can get that u of x is equals to integration from minus 1/2 to 1/2 p at x naught g at x comma x naught to dx. Okay. So, we have exchanged x and x naught. Let us go back one slide. We can see that our g of x is symmetric in the terms that you can switch over x and x naught, where it can be minus x minus 1 by 2, x naught plus 1 by 2, x plus 1 by 2, x naught minus 1 by 2. So, the equations can be flipped. It still remains symmetric. P x naught is our point load or variable point load, where P is the load at that x naught location. So, we can have a distribution of load. Each point has a different load, and say you have the string, and you have say 5 newtons over here, 2 newtons over here, 2 newtons over here, 3 newtons over here, and 3 newtons over here. So, you have a distributed load which is non-uniform. In that case, you can put these p of x naught values, integrate over the domain of x naught from minus 1/2 to 1/2, and you will get u of x. All right. So, with that we have now an understanding of what membranes are. We will take some more problems in the next lecture when we will look for analytical and numerical solutions. But this approach that we have been using so far, we are trying to look it from a perspective of the conservation of linear momentum, that is Newton's second law, force equals to mass times acceleration. There is one more approach that can be used, and this approach is called the energy principle or the Euler-Lagrange method. Okay. So, let us consider the case of our string again. So, we are taking back our old string or membrane. If it is 2 dimensional, it is membrane. Now, instead of doing the conservation of linear momentum or force balance, we are trying to look it from the perspective of energy balance. Okay. So, let us consider the case of a 1D string as represented over here. Now, we assume one, that it is steady state, and second, that the deflection is due to gravity, which is the body force. Okay. So, the string or this thin thread is there, which is being held at the two ends, and the deflection is under its own weight or due to gravity, right. That is one assumption, and second is that it is steady state, and I will show you that where you can make this change. So, any kind of body force will work, it does not have to be gravity, any other force will work. For now we are taking gravity as a representation. Okay. So, the system energy of the system can be expressed as E is equals to the summation of our elastic energy and our gravitational energy. So, energies are always added. The net energy of the system can be constituted into different components, and this is our net energy of the system. Okay. So, it is reasonable to assume that the elastic energy is due to the change in the length of the string, right. So, it is under tension, it is weighing down, it is causing some strain or some displacement in the body. That change in length is what is leading to the elastic energy, right. So, elastic strain energy, you know very well, is half into stress into the strain. So, any change in length or any strain is causing the elastic energy. So, that the elastic energy is proportional to the change in length from the unstretched position or condition or configuration. Okay. So, if the string has a length L, and the deflection is given by u, which is a function of x. So, in the x dimension, again this is the x dimension say, and any deflection is u, which is a function of x. So, in that case we can say that the elastic energy, let us give it by sigma, is equals to the tension on the string multiplied by the change in length. So, from 0 to L square root of 1 plus dy by dx whole square dx minus L, right. So, this is the final length, this is the original length. Okay. So, the net energy that is stored is the tension on the string, this is the string tension. Okay. So, also a proportionality constant, alright. So, final length minus initial length. Our gravitational effects, let us give it by this symbol of g, is equals to sigma g integration from 0 to L y of x into dx, where sigma is a mass per unit length quantity, and g is 9.81 meter per second square, is the gravitational acceleration. Okay. So, sigma into g and that is mass per unit length into, instead of y I should be using u, let me change it to u. Okay. So, u is our display, not the y. Okay. So, these two energies are our net, and therefore, our total energy we can say E is equals to the T times integration of 0 to L square root of 1 plus u prime square dx minus L plus sigma into g integration from 0 to L of u dx. That makes sense? The total energy that we are getting is now a summation of our elastic energy and our gravitational energy. Now, we need to linearize this system. To match with our Navier's equation, that is a small strain approximation. Okay. So, we have linearized our Navier's equation based upon the small strain assumption. That is, we could have taken the Lagrange strain or the Eulerian strain, which had this square term. However, we did not take that, we have taken the small strain or the infinitesimal strain, and likewise we can also linearize this expression. So, the square root of 1 plus u prime square, that is du by dx square, we can make it 1 plus 1 by 2 of u prime. Okay. So, this is a linearization approximation, whole square of this. Okay. So, if we substitute this back into our expression, we can get E is equals to, I will skip one step. So, this 1 plus 1 half of u prime square, this 1 integration over 0 to L dx will give you L. So, L minus L is 1. So, we can take that off. So, 0 to L of 1 by 2 u prime square dx plus this sigma g u dx. Now, we can bring everything under one equation or one integral, that is t by 2 of u prime square plus sigma g u to dx. Okay. So, this is our net energy. Now, our objective of the analysis, and that is a nature's rule, is that energy wants to get minimized. Any system wants to go to the lowest state of energy according to thermodynamics, right, and that comes from the second law of thermodynamics. It will try to minimize its entropy and therefore the energy of the system. Okay. So, the string deflects. So, the deflection of the string goes to a configuration which will minimize the total energy. Now, this process of minimization of a functional, and E is a functional, you can see it depends upon u prime and u. So, it depends on the derivative of the variable, that is an independent variable u, and also depends upon u itself. So, E is a functional, and this functional is a function of functions, right. So, we have two functions, in this case u or sigma g u and this t by 2 u prime square. The minimization of a functional comes under the category of something that is called the calculus of variation. So, this process of minimizing a functional comes under the field of calculus of variations. Some people also call it variational calculus, right. It is a topic which is of tremendous importance when we are doing mechanics, and is something that is worth knowing. Many problems which cannot be solved directly by this linear momentum analysis, variational calculus is an excellent technique. Many of the constraints do not exist in the case of variational calculus and can give you problem solutions to much complex problem. For those who are interested in finite element analysis, finite element tools completely relies on the technique of the minimization of energy by the variational calculus. Okay. So, if that is the case, then we will take it up from the point of the calculus of variations. So, what we will do is that our objective or the idea, the basic concept is to turn the minimizing problem based on multiple variables to minimizing a function of one variable. Okay. Our functional E was a function of x, u and u prime. We are trying to convert this functional into a function that depends on just only one variable. Okay. So, let us take an example for this, and that might be an easier way to approach this. So, assume y of x 1 equals to y 1 and y of x 2 equals to y 2, and consider the function y of x plus epsilon eta of x, okay, in such that where we impose that eta of x 1 equals to eta of x 2 equals to 0, that is the function deviates from the exact solution that is y of x, but agrees at the boundary conditions, at the boundaries. Okay. So, the boundaries are x 1 and x 2. So, our function, the net outcome, it is varying by this epsilon eta x from the exact solution, that is y x. However, at the boundaries where we know, say, plus minus half was our boundary earlier, at the boundary we know the exact values. So, in that case eta x is equals to 0, and we have to modify or find our system based upon this epsilon and eta x. Now, let us write our integrand again. So, integrand last time was E, integration over this t u prime square and then sigma g u. Now, let us write it just as a functional x 1 and x 2. Our functional is given by capital F, is dependent on x, u and u prime dx. For the consistency, let us keep on using u for our analysis, that this makes our analysis simpler rather than changing variables. Okay. So, this is u, okay, u of x. Again over here is u of x. All right. So, our integration is from x 1 to x 2 of our functional f, which depends on x, u and u prime. Okay. U is a function, u prime is a function, f is a function of functions, that is a functional. Okay. All right. Now, we can convert this I in terms of epsilon, we can replace this u and u prime in terms of u x plus epsilon of eta x. Okay. How to do this is integration from x 1 to x 2 f x u plus epsilon eta u prime plus epsilon of eta prime dx. Okay. And we need to minimize our I epsilon at epsilon equals to 0. So, at epsilon equals to 0 is where we are looking for minimization, that is, there is no variation, and that point there should be a minima of I as well. Okay. With that concept, we say that d by d epsilon of I at 0 should be equals to 0. Okay. So, if that is the case, then we can look back into our equation again. This is our f, you are taking a derivative with respect to epsilon. So, you will take derivatives along all of the, let us just take the derivative with respect to f first. So, we will have our terms, that is del f by del epsilon at epsilon equals to 0 will be equals to del f by del y of eta plus del f or sorry, I am using y again and again, del f by del u and del f by del u prime of eta prime. Okay, again all at epsilon equals to 0. If we substitute this back, again let us go back one slide. So, we are taking a derivative of this f with respect to epsilon. Del f by del epsilon is the derivative with respect to the first term, that is u plus epsilon eta, and the second term, that is u prime plus epsilon eta prime. That is what we have done over here. Hence, our di by d epsilon at 0, that is I prime at 0, is integral x1 to x2, and we can then put this value in del f by del u at eta plus del f by del u prime at eta to dx, and this is equals to 0. Okay. So, that is the objective of minimization. We have taken the derivative of our functional with respect to epsilon and we have made it equals to 0. Now, let us integrate. The first term can be integrated as such, and the second term you need to integrate by parts. You have a derivative with respect to your u prime and you have derivative with respect to eta prime. Okay. So, the first term, it will be integration from x1 to x2 del f by del u of eta dx plus, so we will have del f by del u prime of eta from x1 to x2 minus integration of x1 to x2 d by dx of del f by del u prime of eta dx equals to 0. Okay. So, this becomes our net outcome. We can see from here is that this term is equals to 0 at x1 equals to x2 and this term equals to x, I am sorry, this term is equals to 0 because our eta value is our variable. So, eta of x2 minus x1 will be equals to 0. Okay. If that is the case and that is understood for this, then we will take this out and we will have the rest of the terms. So, what we will have is integration over x1 to x2, we can put everything in one bracket, del f by del u for eta minus d by dx, the bracket is over here, of this del f by del u prime of eta dx equals to 0. We can take eta out as common, we get integration from x1 to x2 del f by del u minus d by dx of del f by del u prime of eta dx equals to 0. Now, again we know that eta values at x1 at x2, eta x1 equals to eta x2 equals to 0. That is what we said for eta over here, right. So, if eta values are 0 at x1 and x2 and if you are doing this integration with respect to dx, then this term of this integrand apart from the eta needs to be 0 and that is the condition necessary. So, what we get is that this del f by del u minus d by dx of del f by del u prime should be equals to 0, and this is what we are what we call our Euler Lagrange equation. Okay. So, let us quickly recap on what we did. We had a functional and that functional we replaced our y's with y plus epsilon eta, that is an approximate solution rather than the exact solution. We differentiated our functional with respect to epsilon and we tried to make it 0 at epsilon equals to 0. With that differentiation in mind, we got out 3 terms in which the second term was made to be 0 at x1 equals to x2 equals to x, because eta of x1 was equals to eta of x2 equals to 0. So, the second term became equals to 0. and the first term and third term remained, and we combined them together. Now, since again eta is 0 at x 1 and x 2, this multiplied with this eta within the integrand, that needs to be 0 within the domain of x 1 and x 2. Okay. With that clarity in mind, then we can come up to our string problem. Now, applying this for our string problem. We will get our functional in this case x comma u prime is equals to t by 2 u prime square plus sigma g into u. Okay. Del f by del u, we will get, you can take a partial derivative, first term is 0, second term is sigma g. Then we have our del f by del u prime will be t u prime, and the d by dx of del f by del u prime will be equals to t u double prime. Okay. So, our equation which was earlier del f by del u minus d by dx of del f by del u prime equals to 0. We substitute our variables over here, and what we get is sigma g minus t u double prime is equals to 0, or u double prime is equals to sigma g over t. So, this is a second order ODE and gives a parabolic solution. So, earlier as well we have seen about parabolic solutions with pressure terms, right. It is the same case, instead of pressure we had this gravitational effect sigma into g. T was the tension on the string, and we are getting a similar set of relations. Again we have two boundary conditions, that is u at plus minus 1/2 is equals to 0, right. You can take this, or if you are taking the L case, then u at 0 comma L is equals to 0. Whatever is our set of equations, we can take it likewise. All right. So, this is how we would apply this energy principle to our membranes. Now, we can extend the same analysis for elastic beams. Now, in the case of elastic beams, beam is something like this pen over here. It has a thickness, and the thickness cannot be ignored. Unlike a string, a beam, say a cantilever, has a thickness dimension which is not infinitesimal compared to its length, or a plate is a two dimension of a beam, is something in which the thickness of the plate cannot be ignored compared to the x and y dimension. So, the z dimension has some considerable thickness, due to which our energy term adds up to something else. Okay. So, in the string on the membrane we could do analysis either based upon Navier's equation or based upon this Euler-Lagrange form. However, in the case of beams, our Navier's equation as we have derived will not work. We can remodel or remodify our Navier's equation, of course, when it becomes difficult. So, in the case of beams, because there is this bending action apart from the stretching, the beam is not just stretched, right, it is not just elongated, but during bending certain regions are under tension, certain regions are under compression, and therefore, a concept of flexural rigidity comes into play. Energy methods are much easier to apply for the case of a beam compared to the conservation of linear momentum approximations, right. So, we will use the energy method for this case. So, a beam, consider a paper. So, we can consider an example of a paper which resists bending and returns to the original position on relaxation. Okay. So, this is a beam, it has a considerable thickness delta z compared to its length, that is L. So, in the x direction Lx. So, delta z is not negligible in when you compare to Z. All right. If that is the case, then again from our energy equation, the total energy was a summation of our elastic energy and then some body force energy. As of now, you ignored the body force energy. We will come back to it, or we will add those terms later. If you just look at that there is no gravitational effect, just look at the elastic energy. The elastic energy of a beam is not just composed of stretching. Earlier terms, it was only proportional to the difference in the change in length multiplied with the tension. So, that term is still there, right, and that change in length into tension term is still there, that is called stretching, but we also have a bending energy attached. It is given, say, sigma is now a summation of elastic energy, is a summation of a stretching energy plus our bending energy. Okay, let us give this as SE and this as BE. So, sigma equals to SE plus BE, the stretching energy plus our bending energy. All right. Now, stretching energy we know very well. The stretching energy is tension, and then we have an integration from 0 to L square root of 1 plus u prime square dx minus L. Let us go back a few slides and we can see that this is the same stretching energy that we have been using, integration of the square of the du by dx square dx minus L. So, in the case of strings we just had this stretching example, but in this case, so again let us linearize. So, on linearization, this will be approximated as t by 2 integration from 0 to L u prime square of dx. Okay. The bending energy of a beam is proportional to the linearized curvature. So, as the beam would bend, it creates a curvature along the central line, and that curvature's change when it is linearized is proportional to the bending energy. So, a bending energy BE is equals to E into I by 2 0 to L u double prime whole square into dx. Okay, so this is our change in curvature, and EI is called our flexural rigidity, where E is the elastic modulus and I is the area moment of inertia. All right. Now, we can put everything together into our total energy, and our total energy therefore, total elastic energy is therefore integration from 0 to L of t by 2 y prime square or u prime square plus E I by 2 of u double prime square dx. Now, again if we apply the variational principle, can be applied to minimize the energy, and we can get say that this is a functional from x1 to x2, which is a functional. Now, it is of x of u. Now, there is no u term in this case, but let us take that there is a u term, u prime and u double prime of dx. So, the minimization, if you follow the same routine as last time, as del f by del u minus d by dx of del f by del u prime plus d square by dx square of del f by del u double prime equals to 0. Okay. If you now substitute this value as f, this is our f, we get our equation. As of now, we will get T u double prime plus E I u triple u 4 primes is equals to 0. This is a steady state beam deflection. Okay, this is a steady state beam deflection. You have a double derivative with respect to displacement multiplied with the tension, and you have a fourth order derivative of the displacement multiplied with the flexural rigidity, that is E I. Okay. This is assuming that there is no body force. Okay. Now, let us consider that for a dynamic case, or a transient case, what we will get is that our Lagrangian, for those who do not know, is the difference between the kinetic energy and potential energy. There are three classes of mechanics: Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics. If you can find several lectures online, either in NPTEL or otherwise, which cover these three aspects of mechanics. As of now, you can go back to those lectures and check it up. I will assume you have some understanding. So a Lagrangian L is given by our kinetic energy minus our potential energy. Okay. And we are trying to minimize our Lagrangian, that is a Hamiltonian principle. So, according to the Hamiltonian principle, we are trying to minimize our integration our integrated Lagrangian. Okay. So, we are trying to minimize, what we are minimizing, an integration from 0 to L and from time t1 to t2 of this Lagrangian, which is a function of x and time t, and then u prime and u double prime and others, then u dot, the first derivative with time, second derivative with time, and others, okay, to dx and to dt. And this for minimizing, the derivative of this should be equals to 0. Of this should be equals to 0. So, this is our Hamiltonian principle. So, we find out the Lagrangian. Okay. Now, we know the energy from the last case, that is our potential energy is known. This potential energy is our stretching plus bending. The kinetic energy will come from our velocity and forces. So, from half mv square, proportional to something proportional to half mv square. Okay. So, now we can try to substitute these. So, the kinetic energy Ka is equals to rho into A integration from 0 to L y dot square into dx, or u dot square into dx. Okay. So, where u is the displacement, u dot is velocity, square of u dot is square of velocity, and then rho a is some type of a mass, where rho is the density, mass density, and a is the area. Okay. So, this is our kinetic energy. Now, we can put these terms together. So, again we are trying to minimize this functional. So, minimization from time t1 to t2 and from 0 to L. Our kinetic energy is rho into A into u dot square minus this t by 2 u prime square minus this E I by 2 u double prime square dx into dt. This we are trying to minimize. Again, minimization is the same like we have seen for variational calculus. You have substitute a replacement variable, try to integrate. This equation, it can be minimized as del by del t of del Lagrangian over del y dot or del u dot plus d by dx of del Lagrangian by del u prime minus d square by dx square del Lagrangian by del u double prime, and this is equals to 0. If we do this to our equation, we will get our rho into a into u double dot minus our tension into u double dash plus our E I into u triple dash 4 dashes equals to 0. And this is our constitutive relation for our beam. So, this is our beam model. We can see that it has a fourth order derivative, that means that we need 4 boundary conditions. So, the boundary conditions could be first could be that free ends. So, if ends are free, then at the boundary, now whatever I am writing for these cases are at the boundary. So, at the boundary we will have all u's at u equals to boundary. We will have u double prime equals to u triple prime equals to 0. If the beam is fixed ends, in that case u equals to u prime equals to 0. Then if it is simply supported or pinned, in that case you will have u equals to u double prime equals to 0, right. So, you need 4 boundary conditions. One boundary can be free, one can be fixed, one can be free, one can be pinned, both can be pinned, both can be fixed, or combination of these, right. Then we could have it attached to a string. This u double prime equals to 0 at one end at that end, and minus E I into u triple prime is equals to the spring constant times u. This is your force. Then if we have a point mass attached at end, again you have u equals to 0, u double prime equals to 0, and minus E I u triple prime equals to mass into the acceleration, so m u double dot. Okay, so, the point mass attached. Then we can have a torsion spring. That is u for a torsion u is equals to 0, and E I of u double prime is equals to k of u prime, where k is the torsion spring constant. We could have a dashpot connected or damper. This will be again u double prime is 0 and minus E I u triple prime is equals to c into u dot. And finally, so these are the other types of connectors that you can have. You could use these sets of boundary conditions, and using our differential equation we could try to solve this. So, let us just take one small normalization case. So, if we are normalizing our beam equation, then our beam equation is rho a u double dot minus t u double prime plus some E I u 4 primes is equals to some function that is oscillating this. Normalizing x bar will be x over L, that is the length of the beam, bar is u over b, that is the maximum displacement, and t bar is t over L square root of E I over rho a. We substitute these back, what we get from here is that del square u bar by del t bar square minus alpha of del square u bar by del x bar square plus del 4 u bar by del x bar 4 is equals to some normalized function f bar. What is alpha? Alpha is a combination of this tension and this EI terms. So, alpha is equals to T times A over L to the power of 4 into EI. And what I will urge you is, since you have seen the last lectures, you try to do this normalization yourself and try to figure out how these equations look. In the next class, we will go into the failure criteria and then we will start taking up a few other problems for these beams and membranes and try to solve them both analytically and numerically. And with that, we will finish off our solid mechanics and go into fluid mechanics. And then we have to look at some of the other physics, electrochemistry, electromagnetism, before we step into the multiphysics modeling. So, thank you for listening today.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So, if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So, that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So, we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So, when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.